This is lecture 8 for week 8 of CS 1030. This is the last lecture for this week. And in this part, we're going to look in more detail at logic gates. And we're also going to see how we can build logic gates using transistors. This is pretty cool. It kind of puts together a bunch of elements of what you're learning in a way that I think is sort of very satisfying. So let's look at a NOT gate. A NOT gate is sort of the simplest logic gate. And what a NOT gate does is outputs the opposite of its input. So since a NOT gate has only one input, we'll call it A, there are only two possible states for the inputs to be in. The input wire can either be 0 or low voltage, or 1 and high voltage. And when the input is low voltage, then the output is 1 or high voltage. And when the input is high voltage, the output is 0 or low voltage. And so it has sort of the simplest possible truth table. And let's look at how to build a NOT gate using a transistor. So it turns out that a single transistor can do it, and we build it like this. So let's look at how this works. So remember, the source is always held to the high voltage. It's held to, for example, 5 volts. And so if the input, so now let's look at just go through the lines of the truth table. If the input value A is 0 or low, then the switch is closed and, if the input value is low, the switch is open. An open switch breaks the circuit, and no current flows to the ground from the source. And so the source high voltage is going to hold the output wire high. So if the input is low, the output is high, and the transistor actually, implements that. It makes that happen. If the input wire is high, so if A is high, then that closes the switch. When the switch is closed, then the transistor is acting now like a wire. The current is going to flow from the source to the ground, and the ground, which sort of wins the fight with the source, holds the output wire low. So this starts to kind of connect these different layers of the system. And this is actually how NOT gates really work in real computers. They're actually implemented with a transistor like this. So this is kind of the schematic circuit diagram. And this diagram, it has too many details for most purposes. If we just want to look at the sort of higher level of how the circuit works, we really don't care about the fact that there's an emitter and a ground and stuff like this. We just want to show the kind of logical behavior of the gate. And in that case, we draw what's called a logic diagram. It's a more high-level representation of a circuit than the detailed circuit diagram. And in that case, the NOT gate looks like this. So the input goes into the bottom of a triangle, the output comes out the top of the triangle, and there's a little circle. And we'll see that in several different logic gates, this little circle indicates that there's a NOT operation happening. Okay, so let's look at an AND gate. So an AND gate is a gate that takes 2 or more inputs. Here we're looking at just a 2-input AND gate. And the AND gate outputs true if all of its inputs are true. And for a 2-input AND gate, like we're looking at here, both of its inputs are true. So the inputs are A and B. And since they're 2 inputs, there's 4 possible states that those inputs can be in. They can either both be low, A can be low and B can be high, A can be high and B can be low, or they can both be high. And so remember the trick that we looked at in the last lecture segment of counting up. This is binary 0, this is binary 1, this is binary 2, and this is binary 3. And we stopped counting at 3 because 3 is 2 to the 2 minus 1, where the exponent there was the number of inputs. Okay, so what are the outputs of an AND gate? Well, we already said that it outputs true only if both inputs are true. So if A and B are not true, then the output has to be false. If only one of A and B are true, then the output is still false. And the output is true when both inputs are true. And so this completely characterizes the behavior of an AND gate. And this is one of the most basic fundamental gates that we use for building a computer. So here's an OR gate, another extremely fundamental gate. So an OR gate outputs true if either input is true. And we can generalize an OR gate to have more inputs than 2, in which case it outputs true if any input is true. But we can always build up more larger OR gates using smaller ones. And so let's not worry about that. So let's just look at the 2-input case. So again, it outputs true if either input is true. So if A and B are both 0, that is to say have low voltage, then the output is 0. And we can see that in that case, neither input is true, so the output has to be 0. If either A is 1, or either B is 1, or A is 1, or they're both 1, then the output of an OR gate is 1. Okay, so I hope that was clear. This is super, super, super fundamental stuff. And make sure to ask during recitation or on Canvas or something if any part of this if any part of this slide or the previous slide or the next slide doesn't make sense to you, because we really have to make sure we understand this. So an XOR gate is sort of an interesting one. It outputs true only if exactly one of its inputs is true. So it outputs true if either A or B is true, but not both. So let's look at the truth table for XOR. So it's a 2-input gate, so it has the same 4 lines in the truth table, just like any of the other 2-input gates we've looked at. So if A and B are both false, then the output is false. If A is false and B is true, then the output is true. If A is true and B is false, the output is true. And now the difference between the thing that makes it different from an OR gate is this final line, where if A and B are both true, then the output of the XOR gate is false. And in a logic diagram, we'll do an XOR gate using, it looks like an OR gate, but there's this kind of extra line here. Okay, so again, hopefully this is completely sort of clear. And XOR is sort of, it's a really important operation that we use in building up higher level computations. So just take a second and make sure we understand this. So if I have the A input to an XOR gate being 1 and the B input to an XOR gate being 0, I'd like you to tell me what the output is. And if you don't mind, pause the video for a second, or at least think of the answer in your head. Okay, so the output of the value of X, the output of this XOR gate should be true, or 1, because exactly one of the inputs is true. Okay, there are a few other gates we want to look at. Let's talk about a NAND gate. So NAND means not and. Okay, and so the way an NAND gate works is it's just like an AND gate coupled with a NOT gate. And so the logic diagram symbol for a NAND gate is the same symbol as an AND gate, but we put the little dot on it to indicate the fact that it's a NAND. So it's sort of a flipped AND gate. Okay, so how does it work? Well, we can figure out its behavior by remembering what an AND gate does and then just flipping it. So if A and B are both 0, an AND gate would have output 0, so the NAND gate has to output 1. If A and B are different, that is A is 0 and B is 1, or A is 1 and B is 0, then the AND gate still would have output 0. So again, the NAND gate has to output 1. The last case, A and B are both 1, this is the case where the AND gate would have output 1, but again, the NAND gate inverts it, and so it outputs 0. So it's basically, again, the exact opposite of an AND gate in the sense that the output value is always the opposite of what an AND gate would have done. And the NAND gate is not sort of necessarily fundamental. We could build it by combining an AND gate and a NOT gate. But in many cases, it turns out that building the basic circuit for a NAND gate is simpler than building a circuit for an and coupling it with a NOT. So we end up in practice using a separate logic diagram schematic to show a NAND gate, because they're sort of separately useful. Okay, a NOR gate is, again, very simple. Just like the NAND gate is the opposite of an AND gate, the NOR gate outputs the opposite of what an OR gate would have output. And in the circuit diagram, in the logic diagram, we can see that it looks like an OR gate, but again, we have the little circle indicating that it's a NOR gate. So you could build a NOR gate by taking an OR gate and flipping its output using a NOT gate. But again, it may be sort of better in some circumstances to make a separate NOR gate, and so it has its own symbol. Okay, so let's look at the truth table for a NOR gate. If the inputs are both false, then an OR gate would have output false, so the NOR gate has to do the opposite, which is true. If the inputs are different, then in either of those cases, the OR gate would have output true, so the NOR gate has to output false. And in the final case, if both inputs are 1, the OR gate again would have output true, so the NOR gate has to output false again. And one thing you might wonder is, so how many different circuit diagrams how many different truth tables are there for 2-input gates? And do we have names for all of them? And the answer is there's a bunch, and I don't remember the exact number. And the other answer is we don't have names for all of them. There's a bunch of them that we don't have names for. And if we need one of those things, we would build it by combining gates that we already have, that we sort of have sitting around. So there are sort of kinds of conceptual gates that we don't sort of usually build, but if we did want to, we would combine existing gates, and we could build all of the possibilities. but again, we don't have specific names for them. Okay, so now let's look at something pretty cool, which is how we actually build these gates. So we already looked at how to build a NOT gate. A NOT gate can be built by a single transistor. And remember that if the voltage is high, then the switch gets closed and the output gets pulled low by the ground. And if the input is low, the switch opens and the output gets pulled high by the source voltage. Okay, so that's a NOT gate. So how do we build something like a NAND gate? Well, we can build a NAND gate using two transistors connected like this. And this is really pretty interesting. So let's look at how it works. So if both of the inputs are held high, then both of the transistor switches close and the current flows to the ground and the output is low. So if both of the inputs are high, the output is low. And so I'm going to cycle back a couple of slides. So if both of the inputs to the NAND gate are high, the output is low. And in all other circumstances, we want the output to be high. So now I'm going to go back to the slide with the transistors. So what you can see is in all other cases where it's not the case that both of V1 and V2 are held high, at least one of the transistors is closed, and we don't have current flow across the wires, and then the output gets held high. So hopefully that makes sense. So we can build a NAND gate using two transistors connected in parallel. And what if we want to build a NOR gate? Well, if we want to build a NOR gate, then we connect the two, we can build it again with two transistors, but connect it in parallel instead of in series. So for a NOR gate, so let's go look at which case for NOR we want to look at. So for NOR gate, let's look at the case where both inputs are low and the output is held high. So if both inputs are low to the NOR gate, then both switches are open and we don't have any current flow from the source to either this ground or this ground. And then so the output gets held high. So hopefully that makes sense. In all other cases, there's going to be current flow across either this transistor or this transistor, and that's going to pull the output low. So if we cycle back to the slide, you can see that if either input wire is high or both of them, one of the switches gets closed or both, and we pull the output low. And in the last case that we already talked about, the input stays high. So what this sort of shows is that NAND gates and NOR gates are kind of, in some sense, kind of more fundamental. They're easier to build than AND and OR gates, but they're a little bit harder to talk about using logic. And so we sort of consider those the more derivative gates. But in practice, these may be the more fundamental and easy to build things. And this is a circuit implementation deal that doesn't concern us at all once we're dealing with higher levels of building a computer. So again, this is a really, really, really important slide because it shows how to build logic gates using electronic switches, such as transistors, but of course we could build it using vacuum tubes or relays or whatever we wanted. And this is sort of the bridge, this is the fundamental bridge between the analog world of analog circuits with switches and the digital world where we need to perform logical operations on collections of wires. And so it's going to turn out that using elements like this, we can build everything we need to build a real computer like the one in your phone. And it's pretty cool. Okay, so let's talk about representing gates really briefly. So one way we can refer to a gate is by its name. So we can say X equals A and B. And what you would do if I told you that is you would go and remember the truth table that I showed you for the AND gate, or you'd either look it up or write it down yourself. And now you know what this circuit does. And the problem with this is that you have to already know what the AND gate means. So if you don't already know what the AND gate means, I can just give you the truth table for the thing. This is bulky and inconvenient. So it turns out that sort of both the names and the truth table representation for gates are not necessarily the easiest way. They don't facilitate reasoning about complex circuits necessarily. So we're going to look for a more mathematical notation that lets us talk about circuits and comprised of logic gates in kind of a more concise fashion. And to do that, we can turn to the work of George Boole, who was a 19th century mathematician who invented something called Boolean algebra, which was a way to talk about things that are effectively logic gates, that's to say logic values and logical operations. And at the time, it appeared to have no real practical use. He just did it anyway, sort of like mathematicians do. But then it turned out that Boolean algebra was absolutely fundamental for building computers, and we use it all the time now. And so if you use a computer language like C++ or Java, you'll notice that we have special type of variables called Booleans, and that's where this comes from. They're named after George Boole. Sorry. Yeah. Okay. So let's talk about Boolean algebra a bit. So in the Boolean logic notation, and this is something we'll be using in labs and assignments and exams, so I want you to learn it. We represent the not of a symbol using a little tick, but using an apostrophe. So if x is a tick, we're saying that the value of x is not the value of a. So if a is true, then x has to be false. If a is false, then x has to be true. Okay, to represent and, we have several different symbols, and the symbols are basically the ones we would normally use for multiplication. So either a dot or a times symbol. So if we say x equals a and b using either of those notations, then x is going to be true precisely when a is true and also b is true, and x is going to be false in any of the other three cases. So to represent the or operation in Boolean logic, we use the addition notation. And what I want you to not do is be confused and think we're actually doing addition here. We're reusing a symbol in a new context, and it means something different. Similarly, we're not talking about multiplication in any sense that matters right now. So we're just reusing symbols in a new case. So don't be confused by this. When we're doing Boolean logic notation, we're not doing what you normally think of as addition or multiplication. Okay, so the OR operation represented like this. So what this is telling us here, what we know from looking at this equation is that x is true if either a is true or b is true, or both a and b are true. So XOR gets a plus with sort of a little circle around it. And so in this case, x is true if a is true but not b, or else b is true but not a, and x is false if a and b are both false or both true. And so basically, I'm just sort of summarizing in words what the truth table for the XOR operation already told you, but what this is a more concise way, more concise way to write things down. And what we're going to be able to do is sort of compose equations containing large numbers of these Boolean logic symbols in order to describe much more complex operations. So we could describe something like binary addition or something using this notation. So NAND, we don't have a special symbol for. We just apply the not operation to the and NOR, we don't have a special symbol for either. We just apply the not operation to the or. Okay, that finishes up for this week. We're going to get more into this stuff in subsequent lectures. Thank you.